I'm Kenji Imadera in Kyoto University, Japan. My presentation title is a 5-dimensional plasma turbulence simulation with OpenACC directives. In this talk, after the brief introduction about fusion energy, plasma turbulence, and the importance of HPCs for our research, I would like to introduce our plasma turbulence code GKNET. Then I would like to explain how we introduced OpenACC to GKNET and show you some benchmark tests of GPU acceleration. Do you know most of the energy on Earth is derived from the sun? For example, fossil energy originates from dead microorganisms that have stored solar energy and carbon in their bodies. In other words, we use old solar energy stored in the ground. Solar energy also directly converts sunlight falling on the ground into energy. On the other hand, the sun itself generates huge amount of energy from nuclear fusion reactions. The fusion energy is to generate such a fusion reaction on the ground and create solar energy by our own hands. Fusion energy has been featured as a dream energy source in science fiction movies, but now have been realistic energy resources. In the 1990s, researchers tried to demonstrate the scientific feasibilities of fusion reaction. And in 1996, the critical condition that the ratio of fusion output and input power becomes exactly 1 was achieved, demonstrating the feasibility of such a fusion reaction. And now, in order to demonstrate whether it is possible to obtain 10 fusion outputs from 1 input, a big fusion device called ITER is under construction by international cooperation, and the experiment is scheduled to start in 2025. In addition, there are many countries around the world are currently planning so-called demo reactors to demonstrate economic feasibilities. This is a roadmap of fusion energy. But there are several unresolved issues for the practical application of fusion energy. One of them is called as the turbulent transport problem. I would like to explain this problem by these 2 animations. Left animation shows a donut-shaped fusion reactor sliced in a circular section, tracing the turbulent structure. Right animation shows the plasma temperature along the radial, so namely this direction. In general, the higher temperature can lead more efficient fusion reaction so that we supply heat input around the core region. Let me show you the movies. First, initially temperature increases, but once turbulence is formed, the plasma temperature does not increase anymore because turbulent transport takes place, which converts the heat to outside. So that how to control this transport process is a very important issue, and we try to understand and control turbulent transport by means of large-scale simulations with high-performance computing. On this page, I would like to discuss why HPC is required for our research. In fusion plasmas, there coexist 100 micrometer electron scale turbulence and 10 millimeter ion scale turbulence in 1 meter device size, showing the very clear multi-scale physics nature. In the past, each scale was individually investigated by assuming the scale separation between device size, ion scale, and electron scales. But now, the interaction between different scales are also recognized to play an important role. So we try to do direct numerical multi-scale simulation for device size scale profile evolution and ion scale turbulence to clarify the hierarchical relationship between them by using the following HPCs in our group. Based on such a motivation, we developed 5D plasma turbulence code named GKNET, which can treat both device scale profile evolution and ion scale turbulence. GKNET solves the hyperbolic type 5-dimensional Boltzmann equation and elliptic type 3-dimensional Poisson equations. They are coupled through the distribution functions and obtain electrostatic potential with each other. GKNET has been already MPI parallelized for utilizing HPCs, which parallelization rate is 0.99994. This figure shows good scaling, but this simulation target is a small fusion reactor, and more acceleration is required for future bigger fusion reactor, in which the computational cost also becomes much bigger. Then we introduce the OpenACC directives, which is main concern in this summit, with the aid of Japan, NVIDIA, and QST. And then we verified the efficiency of MPI plus OpenACC parallelization on Marconi 100, shown here, through the Japan-EU collaboration framework for fusion energy. On Marconi 100, each node consists of 2 IBM Power 9 with 16 cores and 4 NVIDIA Volta V100. Memory bandwidth between CPU is 64 GB per sec, while that between CPU-GPU and GPU-GPU is 150 GB per sec by NVLink2. From here, I would like to briefly explain how the OpenACC directives are specifically installed to GKNET. The most heavy part in GKNET is such a 5D loops to time integrate the distribution function in 5D phase space, shown in the red character. We combined these 5 loops to one by using the ACC loop collapse, and then distributed the heavy calculations to each GPU. In this study, for using the multiple GPUs in one node, for example, Marconi 100 has 4 GPUs on each one node. We use ACC set device num subroutine to explicitly link the GPU to each CPU, as is shown in this figure, which technique is available in the MPI-OpenACC hybrid parallelization. For CPU-GPU data transfer, the simple OpenACC data directives such as copy and copy-in are utilized. From the viewpoint of the memory bandwidth, not CPU-GPU data transfer, but direct transfer between GPU-GPU is favorable, but the communication time became worse in our test simulation, so that it has not been installed yet. To check the efficiency of such a CPU plus multi-GPU parallelization, first we tested a simple 3D linear advection simulation, which is a simple example of hyperbolic type partial differential equations as a benchmark. This figure shows the consumed time when we use only MPI and MPI plus 1 GPU per one node, plus 2 GPU per one node, and plus 4 GPU per one node. You can clearly see that GPU accelerated the calculation, which is roughly proportional to the number of GPUs per node. So it is natural to conclude that our method efficiently works for accelerating the calculation of the hyperbolic type partial differential equations, even if we use 60 cores or so on. On the other hand, the collision, so-called the collision part, which is the other main parts of the GKNET, consists of the relatively light 5D 3 loops and 3 MPI all reduced communications. Here, by using the fact that these three variables are independent with each other, the asynchronous execution is utilized to hide the calculation and the communication. More specifically speaking, when a GPU finishes the first 5D loop, it can go to the next executions without waiting for the other GPUs. Same technique is also applied to the boundary part for hitting the buffer set and the communication, and we confirmed that the asynchronous execution efficiently works in both parts. On this page, I would like to show you the resultant computational time. First, by using the one GPU on each one node, the Brazos part is accelerated by 21 times, and the total accelerated rate is roughly 13 times as is shown in this figure. In addition, by using the 4 GPU on each one node, which is the maximum number on Malcolm 100, the total accelerated rate becomes roughly 48 times. The speed up rate from 1 GPU to 4 GPU is roughly 4, showing almost ideal scaling. So we can also conclude that the multiple GPU acceleration efficiently works for the speed up of our 5D plasma turbulence simulation. But FFT part is not GPU accelerated yet, which is the main reason why the scaling of the bound part is not good. We plan to improve this part by introducing QFFT soon, which is a still remaining problem for our development. Finally, let me summarize my talk. To improve the calculation speed and the scaling, we introduced the OpenACC directives, which enables us to utilize GPU parallelization, which is the main topics in this summit. By utilizing OpenACC directives, the calculation speed to time integrate the distribution function was accelerated by 48 times. And now, in the latest version of GKNET, we can already trace such a relatively slow scale ion dynamics, but also the fast scale electron dynamics, which is necessary for the multi-scale simulations. And full multi-scale simulation is not reached yet, but future full multi-scale simulations, we would like to utilize HPCs more by utilizing the OpenACCs. Thank you very much for your attention.